relation between surface energy and surface tension. Let us consider a rectangular frame PQRS. PQRS. And PS is the length, and the surface tension, that force is acting perpendicular to the L. So let us call it, this is the force. So this is in equilibrium position, equilibrium position of the film. It means a soap film is formed between this rectangle, inside this rectangle. So PQRS is the rectangular frame, PQRS, the rectangular frame where the QR is movable. QR is movable. Now the film is developed here, soap film. Okay. Yes, soap film is developed between this PQRS, and QR is the movable one, movable rod, you can say. Thereby you can change the surface area. Do you understand this? So the PS is the fixed frame and the QR is the moving rod. So that you are able to get, you can change the area of the rectangle also. Okay. So a soap film is formed within this frame, like you used to play with a soap bubble, you know. So this is a rectangular film. So a rectangular film is developed here, soap film. Now the film pulls the movable wire, that is QR, due to the surface tension. You would have seen that because of its high, the soapy action, it can move here and there. What we have discussed, the liquid has a tendency to reduce the area. So the film pulls the movable QR due to the surface tension. Take down the film pulls the movable QR inward, that is towards this direction, inward, due to surface tension of the soap film. Therefore, let us call it F dam. So the surface tension is equal to the force applied divided by the length, divided by the length. So in this case, this is L, this is another L. So the force by length means F dash divided by L plus L, that is 2L. Therefore, this force can be calculated as, let us call the surface tension as S. So S into 2L. S into 2L. Now I will give you some time. At that time you can ask. Okay. Now the QR is moved through a distance. QR is moved through a distance by X, by an external force. So let me apply certain amount of force to pull out. Soap film has a tendency to pull inward. Now we are applying certain amount of force to pull outside. So let me draw the same diagram for pulling outside. Okay. So again, you can put the same P, Q, R, S, and this is the L. Now we are pushing outside. We are pushing outside. To what extent? Let me say X distance. So this is the pulled state. Okay, so the distance is here X. So the distance between these two positions is X. It means there is an increase in area. Do you understand this? So this is the X and you have got already 2L into X. That is the increased area. Take down. So this is the first case. Now the second case is that is the QR. Here QR is pulled inside, inward. Now the same QR rod is pulled outside by external force, and let us call that force as F. Now, what is the work done? The work done is nothing but the force into distance. So work done is equal to force into distance. And what distance? This F is nothing but this F dash, that is S into 2L. So equal amount of force should be applied. So I can replace this S by S into 2L into X distance. I can put X. So work is equal to S into 2L into X. And in fact, the because the soap has the film, the side, I mean, it has got two sides. Take down the soap film has two sides. When the soap film has two sides, now, so as I already explained, W is equal to what is that? S into 2L into S. And here it has got the increase in area. Let us talk about the increase in area of the film. So increase in area of film of film. So this is nothing but 2L into S. So we had to input both sides. So that is why we have put 2L into S. X. Now work is nothing but, I mean, energy is nothing but the capacity to do your work. Therefore, surface energy, the surface energy is equal to the work done divided by the surface area. Surface area. So in that case, what is the work done? The work done is available here. That is S into 2L into S divided by surface area is 2Lx. Increase in surface area 2Lx. So 2L into X. So it means that is the surface tension itself. And therefore, the value of surface energy, the value of surface energy, the value of surface energy of of liquid is numerically equal to the value of surface tension. Now, what's your doubt? Then let us move to the angle of contact. 2L. 2L means that is we have got two sides and that is why we have taken 2L. No, 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 no. See, that is this is surface area L and this is the increase in surface area X. So L into X, but it has got two area, upper area and down. So it means we have to consider both the area. So that is why I put 2LX. Now, angle of contact. Here I have mentioned that is soap film has two sides, this side and the beneath, top and bottom. Angle of contact. Okay. Angle of contact. The angle between tangent to the liquid, tangent to the liquid surface at the point of contact, at the point of contact and the solid surface, the solid surface inside the liquid, inside the liquid is called the angle of contact. It means, let us consider here we have the liquid like this, liquid drop. Now, this is the surface angle, that is solid surface angle, and here the tangent to the liquid. This is the tangent to the liquid. So you can have this as S L A, and this is S S A. So here the surface tension, this is the liquid drop. This is the liquid, this is the liquid drop. Now the angle is here, that is this one. This is theta. Wait, okay, this is theta. Now what is SA? SA is equal to the surface tension surface tension between solid and air. Solid and air. And SLA means S, then LA. This is known as surface tension between liquid and air. Okay, so this is a liquid drop and this is the tangent. So it acts tangentially. So this is the surface tension acting uh, between the liquid air tangent and what about this one? This is the angle of contact. Okay, so this is the solid surface where the liquid lies. So this must be the surface tension acting between the solid and the air. Okay, so this is the solid and air, and this is the liquid and air. Okay, so now listen to me carefully. Here we consider this as the angle theta. Okay, and this one is S L. Okay, this one is S L. It means that is surface tension SL is equal to surface tension between solid and liquid. Solid and liquid. Now go through once again. Angle between the tangent to the liquid surface. That is liquid surface at the point of contact and the surface inside the liquid means this one. So it means the theta is supposed to be the angle of contact. Okay. So this is the case with, no, 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 let me finish, then you can ask. When I take some concept, let me finish first, then you can ask because whatever the doubts you are going to ask will be clarified even during the course itself. So that kindly wait. Please no doubt. Then you can, then at the end you can ask. Now, here the value of angle, this value of angle, this theta, okay, theta depends on one, nature of the solid, nature of solid and liquid in contact. Second, it also depends on the cleanliness of the surface, cleanliness of the surface in contact. So this is another important point. Third, it depends on the temperature of the liquid of liquid. Fourth point, it also depends on the medium. Huh? Third point, temperature. Fourth one, medium. It depends on the medium above the free surface. Above the free surface of the liquid. In fact, you could have seen the water that forms the droplets, spherical one on the lotus leaf, right? And that's what I have given here. So this is the lotus, I mean, assuming that this is a lotus, leaf surface on which you have got the liquid drop. So you have got a spherical drop appearing like this. So water forms droplets on lotus leaf like this, while it spreads over a clean plastic plate. So in the case of a plastic plate, it spreads like this. Okay, so how it spreads? It spreads like, for instance, it won't be spherical, as in the case of lotus, it will be spreading. So it will be spreading like this. So in that case, this is the S, SA, this is the S, SL, and this is the SLA, right? So in that case, the angle of contact is theta, so which is acute. But in the case of water, it is obtuse, is it not? So it is more than 90 degree. It is less than 90 degree in this case. So this is in the case of any other surface apart from the lotus leaf. Let me say this is the water on lotus because it has got some micro wax. So lotus leaf. Whereas here the water spread over any plastic plate or plastic surface. Now, at the line of contact, the surface forces between the three media must be equilibrium. Take down at the line of contact. At the line of contact, the surface forces between the three media must be in equilibrium. What are those three media? That now we see. That is solid and air surface, and then liquid and air surface, and then solid and liquid surface. So you've got the surface tensions in all these directions, and there must be some equilibrium. So the surface forces between the three media should be in equilibrium, must be in equilibrium. So now what we can do, the SLA can be resolved. What is that SLA? Can you tell me? What is SLA? Surface tension in the liquid between liquid and air. Okay, so surface tension in the liquid and air system. So this is resolved into two components. A vector can be resolved into two components as what vertical component, then horizontal component. So this can be resolved into that is SLA cos theta and SLA sin theta. What is theta? Theta is the, what is that? Angle of contact. So you can simply say angle of contact. Now, when the liquid on the surface of solid is at rest, so the molecule of these interfaces are in equilibrium. It means the net force on them is zero. That is why I said it is in equilibrium. So it means in the molecule, in this case, let me say, that is, I am considering this molecule. Okay. So at O, take down for the molecule, let me call it O to be in equilibrium. Equilibrium. Here S, SL plus what is SSL? Surface tension acting on the solid liquid phase. And what about SLA? Liquid air. So SLA cos theta is equal to S SA. So please note down this formula. So this solid liquid surface tension and liquid air, that is a cos theta of this component, then it is equal to S SA. Therefore, we can find out the cos theta. How we can find out the cos theta? SLA into cos theta is equal to SA minus SL. Therefore, cos theta is equal to SA minus SL divided by what is that? SLA. And if you are interested to find out the theta, then you can say that is theta is the cos inverse of SA minus SL divided by SLA. Okay, so take down this. Now, the there are some cases. What is that? Huh? Diagram. Particular component means you have to resolve. How you can resolve the component? For example, when you have got one vector, say this, I have drawn this as what? SLA. SLA cos theta. So SLA cos theta means SLA and its cos theta means its vertical component. So you have to take like this. Okay. So this lies in between that. So it must be like this. So let us consider, you have to consider this one. This can be SLA, the other component is SLA sin theta. So vertical component and horizontal component. You have to consider the horizontal component. We call cos theta as the horizontal component. Cases. When SL, SL is greater than SLA. What is SL? That is surface tension at the surface between solid and liquid is greater than the surface tension that occurs between L and A, liquid and air. So this is the case, means it means cos theta is negative. I mean cos theta, cos here theta. This cos theta is negative. Cos theta is negative. And why? Because theta exceeds 90 degree. So when theta exceeds 90 degree, you know, according to all silver T curves. So when it is like this is above 90, right? So here the cosine will be negative here. And that is why I put negative. Okay. So the angle of contact is, and whether it is a 90 and above means then it will be negative. So in that case, the molecules of liquid are attracted strongly. Theta. Molecules of liquid the molecules of liquid are attracted strongly to themselves, to themselves, and weakly to those of solid, and weakly to those of solids. It means as far as the liquid is concerned, this is stronger. So the molecules are attracted towards the liquid, but it is weakly attracted to those of solids. That is molecules in the solids. Those molecules in solids. So it means the liquid does not wet the solid, does not wet the solid surface. And that is why you got that lotus leaf and water system. That is water on leaf. Okay. It is something like a glass on mercury. That is mercury on glass. You can say mercury. Okay. Glass. For example, when you take the glass, when you keep the mercury, it will be forming a spherical shape like this. Similarly, in a lotus flower, okay, you've got the lotus flower like this, and it has got its own leaf. The water on the liquid, water drop on the liquid appears to be what? Non-sticky. So it runs down like a mercury flowing or freely running on the glass slab. So this is mercury, this is glass, and this is the lotus leaf, and this is the water droplet. Appears like a mercury. So they may ask this question, why it appears. So you have to write down all these points as angle of contact. Then second case, other case is acute. So theta is less than 90 degree. In that case, that is SSL is less than SLA. It means this is acute. So acute means it is positive. So here the molecules are strongly attracted, take down, molecules strongly attracted, strongly attracted to those of solid. So solid, attracted to those of solid, and weakly attracted to themselves, and weakly attracted to themselves, that is within the liquid. So you can find here it is just opposite. In this case, molecules of liquid attracted strongly to themselves, okay, but weakly to the solid surface molecule. Whereas here, the molecules are strongly attracted to those of solid, but weakly attracted to themselves. And that is why the molecules here, that is, it is spreading. So when soap or detergent is added to water, the angle of contact becomes small. When soap or detergent is added to water, the angle of contact becomes small. and thereby you are able to spread the what this water bubble along the surface, okay, so that it can be cleansed or removed. So this is the strategy behind the soaping action. So this is a very, very important one. Now you can ask any doubt with regard to the angle of contact. Hmm. Prashant, you have to translate or interpret Shanvi's doubts because I'm not able to hear her voice clearly. Hmm. Hmm. Tell me. Hmm. Now we saw three surfaces. Three, see, for example, when we say that is, I was talking about the solid, liquid, air. Okay. Now the surface tension acting between this solid and liquid. Got it? That is along the tangent because we already know it acts along the tangent only. And what about this liquid air? Okay. Then another chance is that is solid and air. So likewise, surface tension acting between solid liquid interface, then surface tension acting at the solid air interface, and then surface tension acting at that is liquid air interface. Do you understand this? So these all occur in the case of a spherical drop like spherical sphere, in an exact sphere like or something like a mercury drop, or you can say sphere. You could have seen on the what do you call it, the glass plate. It is almost similar to the water droplet that is appearing on the lotus leaf. So you can have a round shape like this. And that is why I said this is one surface tension and this is another surface tension and this is another surface tension. Are you able to follow? So here the angle is wider, more than 90 degree. So more than 90 degree means what I said negative. So the liquid themselves attract too much and there is a weak force, and that is why in this case it appears like a round shape. But when we use the same water in any plastic plate, the angle of contact, that is this sphere, will not be sphere, this droplet. It will be like this. So it is a spread like this, and here in this case, the angle of contact will be like this. So in that case, this is theta and this is theta. So in this case, theta is less than 90. Here, theta is greater than 90. Okay. So when you talk about this, a cos of angle means definitely it becomes negative, whereas here it is positive. Okay. So you are explaining this round shape and the diffused shape of this bubble on ordinary surfaces based on the angle of contact. Okay. And in fact, nowadays they are developing a lot of nano coatings where, for example, you could have seen some surfaces that is called nano surfaces where the water will be appearing like this. It is a totally hydrophobic, so it will run down. For example, when you've got a car windshield, you've got some car here, okay, Now, when they apply this nano coating on the glass, and whenever rainwater comes, it slips like anything, it will not stick to the car. Okay, car that is that the glass. Whereas if it is made up of normal glass, then you can see that is in the normal glass, water will be diffusing like this. So it won't run down so easily. So that is the concept here. Yeah, that is it. It shows that when it is surrounding among themselves means the liquid themselves attract too much, not with the solid, so that it will go down. Mm. Now let us move to the next topic that is called capillarity. Okay, so it's capillarity. Take out. So capilla means capilla means in Latin hair. It means the tube is so fine, very fine, like hair. So a hair like a bore, that is a bore is done inside the tube, inside the solid. So that is why we call it hair. It means capillary means a hair like bore. Bore means some kind of study. For example, this is the tube, normal tube. So you can find the bore here inside which now it is very, very small like this. Okay. And this is called capillary tube. This is normal tube. This is capillary tube. But you can see when you take the cross section, it will be like this. And you can find a very, very small orifice. This is the cross section of the capillary tube. And these are all solid. Do you understand this? So when you keep, for instance, let me keep even not only capillary tube, let me have an setup. So let me invert and it has got liquid here. Now let me keep an inverted jar, a wide jar like this. But when we take, let it be a tube also. And let me say this is a slender tube. You can find the liquid rises up to this. But here there is a very good rise. The height is greater because of the slimness of the tube, small tube. In the case of capillary, it rises perfectly. Okay. So the take out, phenomenon of rise or fall of liquid in capillary. Capillary means a tube of very, very small orifice with a small diameter. So in the capillary is called capillarity. Okay. So what is capillarity? Is a phenomenon of rise or fall of any liquid in the capillary. In fact, we use towels for drying our skin. These are all good examples. And also in trees, they that is the sap, the cell sap, we call it. No, so the sap rises due to the capillary vessels. So these are all the natural phenomena we can explain. Now here, let us talk about this capillary rise. Take down. Let me have capillary rise. So here I got a tube which is kept inside a water which is kept in a beaker. So here air is there and this is the bulk of the solution and you got the AB. liquid inside the capillary. Let me say the pressure, okay, PA externally and here internally, PO. Then you got the height here from the liquid surface. So this is the rise or height. Okay, you can draw another one. Now I am blowing up into a bigger one. Okay, this is the blow up of this capillary tube. So here the meniscus of the liquid is represented, and as you know, this is the theta, and this is also theta. Okay, now uh, this is draw a perpendicular to this angle. Okay, and this is the apparent level, and in between that you got the theta. So this is supposed to be R. Okay, so let me detail everything. And here, these are all the liquid column. This is the liquid column. Now, so one application for the pressure difference across the curved surface is the water rise up and narrow up in capillary tube. It is because of the, in spite of the gravity, you got the gravity means that is downward there is a pull, but in spite of that there is a rise in the liquid level. So we are going to study this capillary rise. Take down. So here the pressure difference between the atmospheric pressure, there is the pressure available above the liquid level and inside the pressure. So the pressure difference PA minus PO. Take down. This is the pressure gradients or pressure difference between the two sides of the meniscus, and this is called meniscus. So the pressure difference between the two, the meniscus, two sides of the meniscus. What is a PA minus P0? The pressure difference between the two sides of the meniscus of the liquid inside the capillary tube. Do you understand this? Is equal to 2S divided by R. It is given by the equation 2S divided by R, where R is the radius of curvature. Okay, R is the radius of curvature. Radius of curvature of what? Radius of curvature of the concave surface. Okay, the concave meniscus. The concave meniscus. So that is called R here. Assuming that now, let me imagine this is the center of the curvature. This is the curve. Assuming that this is the center of the curve, now I can have the radius of curvature. Do you understand this? Okay. So that is called R, the radius of curvature of the concave meniscus. And here 2S divided by R. So the pressure difference is nothing but the 2S divided by R. That is the ratio. You have to memorize this basic concept here. And this 2S, okay. And what about this R? R is nothing but that is R secant theta. Okay, R secant theta. So what is here? What do you mean by cos theta? Secant theta. Secant theta is 1 by cos theta. Okay, take down. Secant theta is 1 by cos theta. 1 by cos theta. Now here, this R is equal to this R, radius is equal to, R is equal to R by cos theta. So can you, that is, identify this capital R? This is the R from here. Okay. So this R by cos theta, it means R is equal to R cos theta. That is, capital R is equal to R cos theta. And you've got two aspects here. What is capital R? Capital R is the radius of the capillary tube. Okay. Take down. This R is, do you understand? This is the center of the capillary tube. And this is R. So you can mention that one also. This R is different. Okay. So R is equal to what? Radius of capillary tube. That is the radius of the capillary tube. And this is R. Okay. This is R. Are you able to follow? And as I already mentioned, this is also, I mean, that is, you have got the right angle here. Okay. You have got the right angle here. This is the right angle. So based on that, you can work out the adjacent angle. So that is nothing but cos theta is equal to R divided by R. Therefore, small r is equal to R divided by cos theta, and 1 by this can be interpreted as R into 1 by cos theta. It means R secant theta. So I can replace this R by R secant theta. R secant theta, that is equal to PA by PA minus PO. Now, so 2s divided by R secant theta. Now this secant theta once again can be interpreted as cos theta also. Okay, so how? Follow me carefully. 2s divided by R, and put secant theta is nothing but 1 by cos theta. Therefore, 2s by R into cos theta. So that is equal to PA minus PO. So PA minus PO is nothing but 2s divided by R into cos theta. Now we are going to apply the Pascal's law. According to Pascal's law, let us consider 2 points A and B. Which are those 2 points? This is A and this is B. Okay. So according to Pascal's law, the pressure must be same at the 2 points. Pressure is the same at 2 points. That is P at A, P at B. They are equal. So in that case, now PA. So PA here, pressure at A is equal to P naught plus the external pressure, I mean PO plus, and this actual liquid pressure. So that is measured by the height. Liquid pressure is measured by, it is proportional to height, and it is a proportional to G also. So we call it P is equal to H rho G. So that is one formula. So in that case, you can replace this. So you can call it P naught plus P H rho G. So that is the pressure head here. So that is equal to PA. That is already equal to PB, which is nothing but the atmospheric pressure PA. Take down. The PA is the atmospheric pressure. Take down. PA is the atmospheric pressure. What is atmospheric pressure? Usually 760 mm Hg in terms of atmosphere, 1 atmosphere. Okay, that is a standard state. Now the PA is equal to PB according to this. Therefore, PA minus PO. That is, we have got this PA, here PO. So bring this PO this side. So PA minus PO is equal to, that is H rho G. Okay, rho is the density of the liquid. Rho is the density of the liquid. Are you able to follow? So PA minus PO is equal to H rho G. Now we have got one important equation here. What is that? PA minus PO is equal to 2S by R. So this is equation number 1. And here we have got another equation 2. Now let us compare the RHS, LHS of these two equations. Therefore here H rho G is equal to 2S by R. Okay. So comparing 1 and 2, H rho G is equal to, what is that? 2S divided by R. So this is a very, very important equation. So from this, okay, from this, the height of the mercury, mercury raised in the capillary column can be calculated. Therefore, H is equal to 2S by R into 1 by rho G. You may ask me, sir, what is the use of these equations? Okay. And we have got another formula also. That is, we have got here this 2s by r cos theta also. So we can substitute here. There are two aspects. So this is 1a, equation 1a you can put. Now let me give this equation also. Okay, so in that case, so let me rewrite PA minus PO that we already seen as 2s by r into cos theta. This is one. Second, what is the next equation we have derived here? That is second equation. PA minus PO is equal to, what is that? H rho G. H rho G. Okay, now we can equate these two. Therefore, H rho G is equal to 2s by r into cos theta. Are you able to understand? So from this, the capillarity. What is capillarity? The height of rise of liquid in capillary. Okay, so the rise of liquid in capillary, capillary means capillary tube, is equal to 2s by r into cos theta divided by rho into g. There is one more application. Using this capillary rise, we can find out the surface tension also. Do you understand? Now you please tell me which are all the experimental value that can be measured. Shanli, which are the parameters that can be experimentally measured? For example, theta is measurable, correct? Angle of contact. Yeah. So this is measurable. And G is the constant. Rho is also the density. And the radius can also be, what is R, capital R? Radius of the capital. So that is also constant, and you can measure using the vernier scales here, micrometer, we can measure. Okay, so this is also possible. And the height of the rise of liquid in the capillary can be measured, okay, using a traveling microscope. Okay, so with the help of that, you can measure, okay, that rise in capillary level. So that is also possible. So using this capillary rise method or experiment, you can find out surface tension. Got it? So we can measure the surface tension using this capillary raise method. So can you rearrange the entire equation? Can you do that? Tell me now. What is surface tension of the liquid? S is equal to, let me call it this as H, right? Okay. H. Now tell me H into R rho H R rho G divided by 2 cos theta. That's it. Okay. So we can make use of this experiment wonderfully to determine the surface tension of the liquid. Got it? So in the next class, we'll be explaining about the calculation part of it, and you've got some problems based on the surface tension entirely. Now, what are the common examples of this capillarity? Take down examples. Blotting of paper. You have got the blot papers, So blotting of papers. It is so fibrous. Okay. So it has got lot of fibrous material, that paper, and because of which it can absorb ink. So blotting of what? Ink by the paper. That is due to capillarity. Second, our turkey towel, or you can call it a towel, turkey towel. So that soaks water on account of the capillarity motion. And also the oil rises through the wicks due to capillarity. So oil rise in what? Lamps, oil lamps. So through the what part? Wicks. Wicks are the what? Threads. They are also acting like capillary tubes. Okay, so these are all the practical examples we can highlight to demonstrate the capillarity. So today we have discussed two important aspects under the heading surface tension. One is what? Angle of contact. Another is capillarity. So you can anticipate a lot of questions based on the concept, reasoning questions, as well as numericals. Okay, so we'll continue in the next class. And what about tomorrow's test? Shall I conduct a complete give you a complete worksheet on whatever I have discussed so far in surface tension? Yeah, I will give you, instead of conducting unit test, I will give you a worksheet, right? Wow. So see you tomorrow. And what time we are discussing tomorrow? I mean, for the worksheet. Why 1 hour? Yeah, we'll make it 5 to 6:30. Why not to 6 to 7:30? What practice? What are you practicing? Huh? Dancing, yeah? Singing, yeah? Okay. What about our Shanvi? Shanvi has gone out of camera. Okay. So we will discuss. I mean, I will give you the worksheet and you can do it tomorrow sharply at 5 o'clock. So 5 to 6:30. Agreed? Right? Okay. Bye.